Okay, as discussed in the previous lecture, the problem with principal component analysis is that while it will give you uncorrelated results, it will not give you unmixed results. And so really, when we have a situation where our data channels are a mixture of independent sources, we really would like a technique that gives us those sources back in their original unmixed form. So as discussed in the previous lecture, often principal component analysis will be done originally to reduce the dimensionality of the data set, but then you still have these mixed signals or mixed variables. So the goal here is to be able, after PCA is done, to unmix the variables into independent variables so that our data set's more meaningful. So one example of independent component analysis is the cocktail party effect. So in the cocktail party effect, you have multiple people who are speaking simultaneously in the same room. So maybe you've got several speakers um, going on, and then you've got a couple of microphones, and these microphones are actually picking up a mixture of both of these speakers. So what you would like to do is you would like to take the signals, which will be mixtures, and have some sort of unmixing that occurs. So the signal that's picked up by microphone 1 is actually some mixture of speaker 1 and speaker 2, and microphone 2 is also some mixture of speaker 1 and speaker 2. And we could visualize this as some kind of mixing matrix that takes our speakers, does a transformation, and gives us our signals. So A is referred to as the mixing matrix. There's physics behind A. In this example, it probably has something to do with the volume of the speakers, the physical location of the microphone, any filtering techniques that are done in the microphone, and the acoustics of the room. So we get this mixed signal. So what we would like to find, if A is our mixing matrix, we want to be able to find A, because if we then take this matrix problem and invert it in such a way that instead of having the signals on the left-hand side, we now have the speakers on the left-hand side, we can do that if we can find the inverse of the matrix A. So basically, independent component analysis unmixes the signals in each microphone to recover the speech of each speaker. Now, the nice thing about this is the technique that we're going to apply, because most of the time we don't know the physical arrangement of the problem. So we don't know what the setup was. And if you think about EEG, we might know there are sources in the brain, but we might not know, physically where those sources are located. So without knowing the physics, the question becomes how to find this matrix A so that we get the independent unmixed signals back. So basically, this is done on making an assumption of how these signals are produced. So the ICA model assumes that your measured signals is some mixture of instantaneous linear combinations of the independent sources. So at any given point in time, we have a mixture at that point in time of signal 1, 2, 3, and so on. And we assume that there are n points in time and that each signal has endpoints. So what we have is we have these x of t's, and I represents, I does not represent time points. I would represent the different signal values. So I would represent like your channels. So we have these I number or n number of measurements represented by subscript I running from 1 to n. And we want to know how out of this set of equations, if we know the x of t's, how would we get our s of t's? So most of the time we will, when talking about independent component analysis, we will drop the time notation because it's sort of implied that it's there. Most independent component analysis techniques don't really care about the ordering of the variable elements. So the fact that S and X are time functions is not relevant to independent component analysis. So in a matrix form, here's what this equation looks like. Our measured values x, then we have these hidden values s, that is what we really want to know what those are, and a is this mixing matrix. So the measured values are referred to as just our measured values are our data set. The hidden values are also called latent variables, and that's because they're not directly observable. So the x values are directly observable. The latent values are hidden within x. So here's an example of a signal mixing. So a data set with 5 observed signals that are linear combinations of 3 different waveforms. Double sine wave, a sawtooth, and a half rectified sine wave all have some added noise. So we'll generate the waveforms using a MATLAB routine. And okay, so here is our original 3 waveforms. And then we take those and we mix them. So here are the mixed signals. The original signals in this case, you absolutely, when you look at the mixture, you can't see what the original signals would look like at all. So this is absolutely like looking at an EEG data set thinking, what the heck do I have going on? So ICA techniques basically are used to solve for this inverse matrix. And if we could get the matrix A, we can invert it and we'll have an unmixing matrix to give us our variables back. Now, the problem is that usually you don't know what A is. So that's what independent component analysis can do. So if we think about it, if we have our measured signals X, and those are basically related to the underlying source signals S by some linear transformation. For example, maybe we do a rotation and a scaling. If that's the case, then we're going to assume that the inverse of that rotation and scaling would recover the original signals. So the goal is how to find A minus 1. To estimate the mixing matrix, independent component analysis makes 2 basic assumptions. One is that the source variables are truly independent, and the second assumption is that they are non-Gaussian. Both conditions are usually met when the sources are real signals. And then a third restriction is that the mixing matrix must be square. In other words, the number of sources have to equal the number of measured signals. That's why it's so important to use PCA to reduce the dimensionality of the data set. So ICA can only be applied. So here are some of the limits. So ICA can only be applied to non-Gaussian signals because it relies on higher order statistics to separate the variables. So if you don't have a statistical background, higher order statistics are often called moments, and we're going to basically create a situation where the higher order statistics of Gaussian signals are 0, so we're going to use this as sort of a test to determine Gaussianity. Since independent component analysis has only the measured values available, there are some limits, and it's very important to understand what the limits are. So independent component analysis cannot determine the variances, energies, or amplitudes of the actual sources. So unlike principal component analysis, the order of components cannot be established. As an example, when we run independent component analysis on the EEG, the raw independent component analysis routine just gives you independent components, but it doesn't do any kind of weighting as to which of those components might represent an eye movement, which might represent actual EEG, which might represent noise. It'll separate them, but then it's up to the person to have some user expertise to determine which components are actual data and which components represent something that we don't consider to be an actual source. So most independent component analyses begin the algorithm with a data whitening. So the whitening steps are, first of all, you take the data set and you center it. This usually involves the subtraction of means. You then decorrelate the data using principal component analyses, And then you scale the data so that the variances are all equal to 1. And so the whitening operation is often known as sphearing the data. So here's an example of before and after data whitening. The unmixing matrix is then determined by optimizing some kind of objective function related to the independence of the data. Lots of independent component analysis algorithms have been used. A lot of them are available as downloadable MATLAB files, and they basically differ in two ways. First of all, the objective function that's being optimized, and secondly, the optimization method that's being used. Usually, these are based on what your data set is, and some techniques work better than others, say for different types of data. So the main optimization criteria that's typically used is to use an objective function that's related to the non-Gaussianity of the data set. And this takes advantage of the fact that mixtures tend to be more Gaussian than the distribution of the independent sources. So mixtures of non-Gaussian sources will be more Gaussian than the unmixed sources. So let's look here at that. So mixtures of signals will have distributions that tend to be more Gaussian than the real signal. This is because of the central limit theorem, that as we take a sum of k independent distributed random variables, it's going to be converged to a Gaussian distribution as k becomes large, regardless of the distribution of the independent variables. So, for example, the distribution of a single sinusoidal function is very non-Gaussian. Here's a Gaussian distribution. Here's the distribution function of a single sinusoid. You can see they're quite different. But now even two sinusoids mixed together, you see we begin to sort of approach a more Gaussian distribution. As we have four sinusoids mixed together, even more so. So we would expect our data sets, since they're mixed, to have a more Gaussian distribution than our latent variables that are hidden within that. So one approach to determining how Gaussian a signal is to use a variable known as kurtosis. Kurtosis gives you an indication of how close the shape of your distribution function of your data set is to Gaussian. It comes out of information theory and statistical methods, which we won't go into detail in this class, but I can provide you with some resources if you're interested. Kurtosis is one of the moments associated with the statistical analysis. So, for example, here is our original signal, and here is a whitened data set. You can see that if we plot a distribution function here, we have the red and the blue, and then once we whiten our data set, you notice we have increased the width of those distributions. If we now use an algorithm called fast ICA, fast ICA is working to separate the signals. So after the first step, watching the curve here, you see that it is becoming less Gaussian shaped. After 2 steps, after 4 steps, watch what's happening here to the curve. And finally, the final rotation, you can see that we have quite a bit of difference. What has happened is fast ICA has pulled out a sinusoid here. And as you can see, the distribution looks like that sinusoid distribution that we showed on the first slide when talking about Gaussianity. So we have our original signals. Here's what our separated signals look like after 5 steps. I will tell you that in a typical routine to run ICA on a 60 channel or 65 channel EEG system, probably 300 to 400 steps. And what happens is the steps are highly dependent upon sort of the initial condition assumption of weighting. So within a good independent component analysis technique, you assume that there are some weights associated with the mixing, and you have to have a starting point to do this iterative algorithm. So how you assume those initial weights are distributed in your mixing matrix can directly affect the outcome. So what I'm trying to say here is you can run independent component analysis 20 times. You will get 20 different results. So you get a non-unique result from ICA. So a couple of popular algorithms online. The fast ICA is the one that's commonly used for EEG. The JADE algorithm I have not seen used as often in EEG, but it is implemented here. So W is your unmixing matrix, X is your data matrix, new ICA is the number of components desired. So at first glance you might say, well, this is reducing the dimensionality of the data set. Yes, sort of, but ICA is a much more efficient algorithm to run if you have already run PCA. So here is just an example of the application of the JADE ICA algorithm using that mixed signal that we previously created from the three components. So initially PCA is applied. Here's showing your table of variances indicating that there are three components of significance if you use a cutoff value of 5% and zero out everything else. Here is the scree plot also that indicates we probably have three variables, at least two, possibly three separate components. After independent component analysis is applied to that mixture, you can see that we do generate a pretty good representation of our original three components that we used in that mixture. There's a couple of differences. One is the amplitudes are modulated. And so independent component analysis excuse me, does not give you any indication of the level of energy contribution of the different components. So when you do this unmixing, a lot of times it'll do really weird things with your amplitudes. And that initially can confuse people, but you can't give any physical interpretation on the ICA signal amplitude. So as previously mentioned, one good example of independent component analysis is this separation of different sounds that have been mixed by different sources. So if you look at this particular little graphic, basically you've got a speaker, some background music, and perhaps a siren in the background. Those are all mixed. When you unmix them, you do get the original sources back, but they may be ordered in an odd way. So this is what I was saying before. This now requires the individual to evaluate. Let's say you wanted only the speaker's voice. You will have to be able to evaluate from the signal that these other components are components that you're not interested in, focusing only on this one. So a biomedical signal processing example might be that you're interested in identifying eye blinks from a set of EEG data. When you do a decomposition, an ICA decomposition of data, then basically what you're looking at is you're looking at the components, and you have to be able to recognize which component is the eye blink. Now, if you then want to reconstruct the data set into your 64 channels or your 60 channels, you actually can come into your weighting matrix and you can zero out the components associated with undesired physical effects. So one way to remove artifacts from a data set is to do independent component analysis, get the components of the data set the ones that you don't want present in your data equal to 0, and then you can get theoretically your data set without that artifact present.